But the time is over. For the next lecture, I haven't finished at this moment.
Our last speaker this morning is Professor Jerry Smith from Southern Illinois University. Jerry is professor of chemistry and the director of molecular science program there. He received his PhD in 1956 at the University of Arkansas. His current research interests include work in cold chemistry and catalytic hydrogenation, and in addition to that, work on enantiomer selective catalysis. This morning he's going to be talking about hydrogenation and exchange of alpha-beta unsaturated esters over deuterated Raney nickel. Jerry?
Thank you. First of all, I want to thank the organizing committee for the opportunity to be here and present this. I appreciate it. It's good to visit with old friends. I was able to participate in the first such conference, and I'm delighted to be here again. I have a couple of announcements to make. One, you'll notice if you listen to Al that the talk I'm giving is not the same as the title that he gave. But don't let that bother you. It's still on catalytic hydrogenation. I asked Jerry if I could substitute a different talk. He said, fine, no problem at all. Yeah, so I did. The abstract is correct. It's just that the title is the original title. So, well, second announcement is I wonder if Gary moved his chair back. Al's been kidding me a lot about going to sleep this afternoon. I want Bert to get some pictures of him going to sleep during my talk. Well, I want to talk about double bond isomerization. We've been working in my laboratory for some time with small metal particles. And first thing I want to do is kind of bring you up to date on this. Let's see, how do you push the clips in? Here we go. Okay, so I've got to talk in about three different categories here. First of all, something about small metal particles and some recent information that you find in the literature, which might be a little controversial, but nevertheless, it's something that's going on out there. Second is the molecular probe apopynine, the molecule that we have been using to try to tell us something about the surface and what it's told us, or what we think it's told us. And the third thing is something about the double bond isomerization and how this seems to give us some information about migration of surface hydrogen and deuterium over these small metal particles, particularly the smallest metal particles. Now, to get everybody in the same line of thinking, and this is probably going to be kind of old stuff for most of you, but metal particles seem to have essentially three different kinds of sites on them. Some of them can be divided into other subcategories, but basically we have corner sites, which Siegel has called 3M sites, and others have called a type C type site. Add atoms also fit in that category. Edge sites, which you see along here, which Siegel has called 2M sites, and planes or terraces, if they're on a sliced metal, which are called 1M sites. And this nomenclature comes pretty much from the work of Summerjai and his colleagues, and you can see the same sort of things. If you take a single metal crystal and you slice them at different angles, you can produce either just edges or you can produce a lot of kinks, which are corner type atoms. Now, real catalysts that are used in the industry don't look like that, but they're tiny little metal particles. Please ignore this business about all kinds up here. If you transfer the information or the ideas from the single crystals to the metal crystallites, which we think are on catalysts that are being used in industry, Then we have things like cuboloctahedrons and even smaller such species. As you can see, these parasites will have an analogous on the planes of this little crystallite here, and in the center right here, the kinks are the corners. You see, and here's a molecule or an atom particle with practically all kinks on it, and so forth and so on. So I think that the analogy, at least the nomenclature, fits both systems. But we've been making a lot of different catalysts, platinum and palladium catalyst particles that have very small size. Now here's an article by Hartefeld and Hartog describing some more information about these particular crystallites, and I've gone to the trouble of dubbing in on the same sort of slide here the population, their calculations of the populations of these different kinds of species. For example, planes, these are the largest particles over here. These are the smaller particles, and this distance is plotted here as a relative number of unit cells, I believe. Well, the edge sites, you see, go to a maximum, and the corner sites go up like so. Now, on these truncated octahedra or these cuboloctahedra, it's a little bit different. The edge sites come up like so. The plane sites, of course, decrease, and the corner sites go to a maximum when you get really small. Now, this is an interesting structure. What has happened here is you can see there's an overlayer, a partial overlayer of another layer of atoms, and that gives you like some corner atoms, like right here's a corner atom, and a whole row of edge atoms. And when you plot those, these two are the edge atoms, they go up and go through this pretty little thing here. So I just want to point that out to you because some of the data I'll show you later on from the apophytine work kind of correlate with some of those. Now, recently, a fellow named Rich Mossell at University of Illinois has been doing calculations on these small metal clusters. He's also been doing some experiments trying to make small metal clusters and do some analysis on them. And he's come up with a rather interesting phenomenon that when he makes calculations on these small metal clusters, they don't come out to be regular crystallites. They come out to be some misshapen sphere. Now here's some lowest energy structures that he has come up with for platinum, and here's 20 atoms, and you see that's doesn't look anything like a regular structure. Here's 40 atoms, and these are just represented, but you can see they're all misshapen. And he's done the same sort of thing for palladium, and this is what these things look like for palladium. A particularly interesting thing with palladium is that the structure looks kind of what he calls a cigar-shaped structure. You see it's kind of elongated along this axis. Now he cites some experimental evidence that he's found out in the literature from some scanning tunneling microscopy studies, which do suggest that these things are spheres, not regular structures, not regular crystal structures, and that they are misshapen, although this evidence may be kind of sketchy. Nevertheless, this idea has been introduced into the whole work that has to do with the use of small metal crystallites. And Professor Mossell tells me that he has been unable to make catalyst particles smaller than 20 angstroms that retain some kind of a regular shape. He says above 20 angstroms that they do get regular shapes, and he is able to get some reproducible results on these that correspond with regular shapes. But below that, he doesn't, and so he hypothesizes that the reason is that these particles don't have regular shapes, and therefore and they're flexible, and they maybe are in constant motion, and therefore they don't give catalytic reactions, give results of catalytic reactions that are consistent with what we would call regular shape. So this whole idea has been introduced here, and I want to show you a little bit later on how this seems to explain some of the results that we've been getting for about the last 10 or 15 years. Here's an example of a clean palladium cluster with 13 atoms. This is the smallest regular structure. He adds a hydrogen to that, or adds hydrogen to that, and you can read what he's got here. He gets this cubic type structure. Now, apparently there's some dispute as to whether his calculations are all that valid, but nevertheless, this idea is kind of a new paradigm as far as I'm concerned, and it makes me think different ways about how to explain my experimental results. Now, so that's the first part of the talk. The second part of the talk is I want to tell you a little bit about this neat molecule that we've made and that we've been working with for quite some time. This is a molecule that's called apopynine. I don't know why it's called apopynine, but it is called apopynine. I suppose because it comes from a molecule that's named pinene, and apo, I guess, or the apo has something to do with the loss of something, but we take a methyl group off of pinene and you get apopynine, so here we have apopynine. This, I believe, is a minus isomer. If you look in the abstract, I got this labeled as a plus isomer. I discovered to my horror just before coming over here that it looks like one of my students' dissertation, he has it marked wrong, but it doesn't really matter as far as the whole argument goes, except for cleanliness. Now, you'll notice that you have here a carbon-carbon double bond, and here you have a carbon next door which has two allylic hydrogens on it, one up and one down. And the reason why I have this blue and this red is because we have, at the end of the talk, I will show you that we have substituted deuterium in one case here, and in the other case, we have substituted deuterium here. So we've got these two molecules, and we run hydrogenations with them. This thing has this real neat umbrella type thing above the top of it, which is real bulky, this gem dimethyl group, and these block, essentially, sterically block the top side of the molecule. So you would hardly expect it to absorb on a surface with this blue towards the surface. So we believe it absorbed on this face, and down here you see you have a methylene with just two hydrogens there. And we've done a lot of work on this, and the last student to work on this did the NMR of the entire molecule and identified every single carbon and every single proton in it by using 500 megahertz NMR. So we know quite a bit about this molecule by now. Well, one of the things that we found was really, well, before I do that, I'll tell you a little bit about how we get information. Why is this molecule neat? Why is it so good? Because you see, on a symmetrical surface, its double bond isomers should react at exactly the same rate. So if the surface is symmetrical and not asymmetric, then this molecule should go back and forth if the double bond can isomerize. But both of these should hydrogenate at exactly the same rate. So we don't have any problems with that kind of thing. And this is one of the problems we had with previous probes, was that the daughter of the isomerization would hydrogenate at a different rate from the parent, and therefore exclude the parent from the surface and confuse everything. So we couldn't analyze it. This is just showing how we make the calculations, and what we can get is a ratio of isomerization to addition out of this whole thing. This is something that you can do if you hire some good physical chemists to make these calculations for you. Then you can concentrate on the organic chemistry. Now, when we hydrogenated this molecule over some platinum catalysts that we got from Burwell and Buck's laboratory at Northwestern University, that have been well characterized all over the world in several different laboratories, what we found is this ratio of the rate of isomerization, or the Ki to Ka, which are pseudo rate constants, but they should represent roughly the rate of isomerization over the rate of addition. varies according to the percent dispersion of the catalyst, the smallest particles being over here at 100% dispersion, varies and goes through a maximum at around 60% dispersion. Now I want to point out to you at this stage that from about 60% dispersion on, particles are probably smaller than 20 angstroms in size, 25, 20 angstroms in size, which would agree with what Marcel has been saying about these small metal particles not having any definite structure. We have believed for some time that this curve corresponded to the edges on these small metal crystallites. And the reason for that is that if you plot in this way, and remember I had plotted earlier in another way, if you plot the fraction of edges and the fraction of corners, you see, and these are the fraction of edges on this crystallite, cubo-octahedron crystallite that had overlayers of partial overlayers of metal atoms on it. And you see it goes through a different maximum here than this maximum here. But if you overlay on our data on this particular figure, you see it goes through a maximum, and the maximum, well, is somewhere in between here, but you can rationalize, well, the crystallites, we've got our range of crystallites, there are a range of sizes, and so maybe we got some kind of an average between imperfect crystals and perfect crystals in there, and this is what we're seeing. Now, I want to throw out the idea that perhaps the reason why this decreases here is because we have some very, very tiny particles in this range, which do in fact not have regular crystal structures and therefore are not catalyzing the reaction very well. And so there's a drop-off in this part of the spectrum. Now we've gone on then beyond that, and we've done more work with new batches of catalysts. Here are some data in which we've correlated not Ki over Ka, but the turnover frequency for addition with particle size, and you can see they go through maximum right around 60% exposed, just like Ki, Ka. And so that means, of course, that isomerization also goes through a maximum on these particular sizes. Now, we thought we were getting real clever, and we found that poison, carbon disulfide, poisons these reactions. And it poisons them fairly linearly. So if we measure the rate of hydrogenation, say, and put in very tiny amounts of carbon disulfide at very dilute in solutions, and we count the number of carbon disulfides we put in, if we know how much catalyst we have in, we know the surface atoms on the catalyst, we can count the number of carbon disulfides that we've gone in, that we put in versus the number of exposed metal atoms, and we can essentially titrate the active sites. And these are just carbon disulfide active sites. They're sites which whatever carbon disulfide sees, but they do poison the hydrogenation. It stops down here. And if we take these endpoints, that is, how many carbon disulfide sites there are on each metal particle, and we plot that versus dispersion, you see we get the same exact curve. In fact, it turns out that there are the number of carbon disulfide or the sites per metal particle correlates with the dispersion. Now, if you get a little correlation here. My hand. Going too fast. I don't want Al to stand up. Oh, he's awake now. Better be more careful. Now, if you, interestingly, take the turnover frequency for addition and plot that against the number of carbon disulfide sites, you get this interesting plot here for all of the catalysts we've studied. And the slope of this line is 17, which suggests that the turnover frequency per active site for all of these catalysts is 17 per site per second. Now, take that piece of information and this next piece of information, and we'll come up with a new mechanism here. Not only that, when you're titrating with carbon disulfide, the Ki over Ka ratio essentially does not change. That means when you poison with carbon disulfide, you poison both isomerization and addition at the same time. Now, how can that be if they are occurring on different sites? Well, obviously, that doesn't make good sense. So we came up with an alternative mechanism for hydrogenation, and that is that the isomerization reaction is rapidly going on edge sites, that hydrogen is dissociating on edge sites and migrating over to the planes where it is catalyzing hydrogenation. Now you'll notice that I've got two different kinds of isomerization here. I'm going through what this is essentially a half hydrogenated state isomerization. This is what looks like a pi allele isomerization. What I want to concentrate on for the rest of the talk, which obviously is going to be rather fast, is the isomerization reaction, as Al is now fully awake. We had originally thought, because when we did the isomerization of this molecule, we did not get much deuterium in, that this kind of a isomerization was forbidden. And so we postulated this 1,3 over the top kind of isomerization. It turns out that when we labeled the molecule with deuterium, in fact, what we found was that the hydrogen, in this case, hydrogen migrates over the bottom to give us isomerization, and when we use deuterium, hydrogen still migrate across the bottom. We got very little deuterium coming in here. When we put deuterium in this position, we got deuterium over here, which means that we have a 1,3 bottom shift occurring, rather than a 1,3 top shift or any other kind of a thing going on, and that's going on very fast. So this leads to a whole new line of thinking as far as the mechanism is concerned, and it fits in with the mechanism proposed by Anderson, and that is that if he did some calculations with propylene, and he put propylene down, and you see, and he pulled off an allylic hydrogen, and there it is resting on that atom, and then he shifts this adsorbed species over a little bit, and he adds the hydrogen back to the other end. So it's a 1,3 shift, but using the surface. Well, obviously, apopynene can't undergo that shift because it doesn't have a hydrogen in this position. It has a hydrogen in this position. So there's some question about exactly how that migration is going to occur, but there's no question but what it occurs on the surface. Now, finally, last 25 slides, finally, I want to talk a little bit about some deuterium exchange of just the light apopynene molecule. Now, this particular student in this particular work I'm talking about did some studies where he exchanged and looked at the amount of deuterium going into the molecule, which goes in rather slowly. When he did that, he got this for two different kinds of catalysts. He got this, and this is really, really interesting, I think. One, on the large particles, he got this interesting curve. I got this red thing kind of dubbed in there. The other one, the black line, is what a computer did, but you know, computers, they do any old thing. And if you take a pencil, you can do a better fit than the computer. But on the small particles, you notice the deuterium entering into this molecule, the small particles, is much slower. than it is initially on the large particle. Now, to show you that that's not, because he's only got a few data there, to show you that's not a bunch of nonsense, we do have some experimental verification of that. 20 years ago, when we first made this molecule, we did deuterium incorporation, and you can see what the computer does there in the dark line. It thinks that every point's important. But if you take these two and figure out how to put them together and overlay them, you'll see that the same sort of thing is happening. Now, on the old data, we probably had a catalyst that was about 12% dispersed. Last two slides.
Don't forget, I will be standing behind you in a moment.
That'd be interesting to see. It hasn't happened yet. In the earlier work, we found that the exchange versus addition is about 1.5, and the exchange versus isomerization is about 0.6. In the present work, we have large particles, and we get about the same results. So I conclude that on large crystallites, exchange is faster than addition but slower than isomerization, except initially the exchange and isomerization occur at approximately the same rate until deuterium is depleted in the vicinity of the active sites and more deuterium must migrate in. Then exchange is surface diffusion limited. And finally, when we compare the large crystallites to the small crystallites, I think this is really interesting. You see on the large crystallite, we had isomerization versus addition, the ratio about 2.6, and in the present work over a different catalyst, it's about 2.5, so they're about the same. On the other hand, the isomerization versus the exchange is dramatically different. And so this, I think, tends to support the idea that these small metal crystallites are, in fact, quite a bit different than what we had been thinking about before. Thank you.
We'll open the floor up for a discussion at this time. Any questions?
Jerry, on your double bond isomerization, your labeling experiment clearly indicates that the allylic shift is occurring. Can you also then exclude which was the adsorption, desorption shift to the more classical time kind of mechanism? On your particles, you showed us both. And,
as a matter of fact, we believe that the classical mechanism is going more slowly than the high-allyl type, but it is going on. You see, we do see some, if you probably didn't catch it and I didn't point it out, but in the one transparency where I showed the we're getting to it now, where I showed you see that we had some other species in there, and these can be coming from the classical type isomerization, where we're pulling off a hydrogen, putting a deuterium in, you see, and then it's moving around and things like that. So in fact, there is some evidence, but they start appearing rather slowly later on in the reaction.
Professor Smith, please explain us. You demonstrate direct evidence about when hydrogen react with small particle size, small particles, all the surfaces are rebuilding. And then I have a question: how you account for this phenomenon in your calculation when you correlate the number of various kinds of kings, edge, and planes on your small particles? Thank you.
Thank you. I think the only evidence we have that edges are involved is the fact that we get this increase up to this maximum, and so we're assuming that that's due to edge sites. We don't have any proof other than the experimental evidence. One of the things that may be happening, of course, is that the surfaces of these metal particles may be reconstructing when you put hydrogen on them, and a reaction is going on, and then when you remove the hydrogen and the substrates, they go back to their original shape. And I think that's a distinct possibility, which I don't know how we would prove except to try to look at these metal particles immediately before we run the reaction in situ, then after we put hydrogen on them, then after we put the organic molecules on them, and I'm not sure that anybody's gotten quite that sophisticated yet, but that's got to be the next step.
Any other questions? Well, if not, I'd like to thank our present speaker and the two preceding speakers then for their presentations in this morning's session. Thank you.
Let me have an announcement. The launching is